You're feeling pretty confident about those balancing chemical equations, are ya? Let's get into a challenge then, and put your knowledge to the test. By the end of this video, you should be able to use balancing strategies to combat any kind of balancing chemical equation challenge that you may encounter, including those nasty combustion reactions, which tend to be the most challenging out of any of the equations to balance. Just as a reminder from our previous lesson about balancing chemical equations, just remember that we are only manipulating the coefficients, never the subscripts, and it takes a lot of practice to kind of get the hang of these. So don't give up right on the first bet, especially if you don't see the pattern right away. That's okay. Just keep trying. Just keep trying. Just keep trying. Plug and chug those numbers in, plug and chug the coefficient multipliers until you end up balancing all the atoms. The important thing here is bookkeeping and making sure that you're keeping track of all your multiplied new numbers every time you change a coefficient. If you do that successfully, you'll get there eventually. Here's our first challenge question. I challenge you to pause the video here before I show you the answer. If you're not willing to take that leap quite yet, that's all right. Let's work through this one together. Just like with the previous balancing chemical equations that we worked through in our last video, we're always going to compare our products to reactants first. We need to see what atom types there are, and we always need to start on the product side just for the sake of knowing a spot to start. So let's draw a line through the reactant and product side so we know we are comparing one side to the other all together. And now let's document what atom types we have present. We have carbons, we have oxygens, and we have hydrogens on both sides. Let's count up how many there are to start. On the product side, we have one carbon, and there's no carbons in that atom. So we've got one carbon total. We have two oxygens here and one oxygen there. So we have three oxygens total on the product side. Again, it doesn't matter that they're in two separate molecules. We're counting up how many atoms there are overall on the product side. And hydrogens, we have two. How about the reactant side? We have one carbon, we have four hydrogens, and we have two oxygens. Now when we compare across, we can see that our carbons are currently balanced. Awesome. Our oxygens are not, and neither are our hydrogens. As mentioned in my previous video, anytime you have a value that has an odd number, like 3, and an even number, like 2, that's the one you want balanced first for any of the ones that are unbalanced. Let's start with our oxygen atoms in terms of balancing this chemical equation. Just as a reminder, we're not manipulating any values in the subscript region. So I can't just put a 2 here and now I magically have two oxygens, and then I'd magically poof have 4 on this side. I can't manipulate the subscripts. When I just did that, I created hydrogen peroxide. Side note here, two gentlemen walk into a bar. The first orders H2O. Waiter says, awesome. The second orders, oh, yeah, I'll take H2O too. And the waiter says, you sure? Person number 2 says, yeah, obviously. And drinks H2O too and dies. So H2O2 is not the same thing as H2O. We can't put a subscript there. That will change the molecule itself. However, we can put coefficients in front to change how many molecules of water there are or how many molecules of carbon dioxide there are. Now, the whole goal here is when we have this odd number and this even number, trying to make it even. So let's just show you what would happen if I put a 2. I'm always usually going to start with a 2 or a 3, and you kind of work your way up from there. It's kind of like solving a puzzle. You just plug and chug and see what works. So here we have 2 carbon dioxide molecules now. So we've got 2 whole molecules of CO2. And when I do that, I now have 4 oxygens plus 1 oxygen from water. So that still gives me an odd number. It still gives me 5. So 5 as my oxygen count still doesn't get us any closer to having both oxygens on both sides be the same number. We need to get them to either both be odd or both be even. So obviously manipulating the CO2 at this point in time isn't very helpful for us. So how about instead I put the 2 in front of my H2O, my water molecule. Now that 2 can distribute into the H2O water molecule, just like in math, where you have anything in parentheses and it multiplies by everything inside. So now I would have 4, 2 times 2 down here, hydrogens. And in the water molecule, I have 1 oxygen, so 2 times 1 would give me 2, but don't forget that there's still 2 oxygens in the carbon dioxide. So now on the product side, overall, I have 4 oxygen atoms. Now let's go over to the reactant side and see if we can balance those oxygens accordingly. We do know that on the reactant side we have 2 oxygens, and 2 does go into 4, so if we can create 4 somehow, we're in good shape. Again, I can't just take this 2 and change it to a 4 and call it dandy. That would be one really weird looking molecule. First of all, oxygen looks like this, O2. And then if I shoved a 4 down there, that would somehow be forcing oxygen to do this. So don't mess with the subscript numbers, ever. All right, but what I can do is I can put a 2 in the front as my coefficient, and now 2 times 2 would give me 4, just like on my product side. Awesome, so here my carbons are balanced, my oxygens are balanced, and by doing that, I've also balanced my hydrogens. It just happened to work out that way. Awesome. So my balanced equation would now look like that. Ta-da! All right, now seriously, you should pause the video at this point. Now that you've seen one done, pause the video and give this one a try. See if you can balance this challenging combustion reaction yourself. Ready, set, go. All right, want to know if you got it right? Let's try it together. Draw that line through our product and reactant side. Let's list all of the atom types present. We have C, H, and O again, and that's always going to be the case for our combustion reactions. C, H, and O are always present. On the product side, I have 2 H's. I have 1 oxygen here and 2 oxygens there, so 3 total. And I have 1 carbon. 1, 2, 3. Oh no! I also have 3 carbons. Now how about my reactant side? I have 3 carbons over here. I have 8 hydrogens, and I have 2 oxygens. Now let's compare both sides to the other and see if anything's already balanced. Well, we have 3 to 1, 8 to 2, and 2 to 3. So in this case, none of them are balanced. Ay chihuahua, we got a problem. We need to pick one of these unbalanced atoms to start with and go from there. Personally, I like to start with oxygen in this case because there's still that odd value with an even value. Notice for hydrogens, those are both even numbers, and for carbon, those are both odd numbers. Anytime there's an imbalance of odd or even, that's typically the one you want to start with to make the rest of the balancing easier. So we'll focus on our oxygen first, and let's focus on the product side. Just like before, if I would start by manipulating the CO2 oxygen, I would have 2 times 2 for the oxygen. I would have 2 times the carbon, which would give me 2 carbons. And I would have 2 times 2 for the oxygens, which would give me 4 plus the 1. So I would still end up with an odd number. That's not helping my situation any. So I'm going to jump ship on putting the 2 in front of the CO2 and instead manipulate the number of atoms that I can get from molecules of water. So let's put 2 in front of water. So now if I distribute that 2 in, I end up with 2 times H2 and 2 times 1 for the oxygen atom present there. That gives me a total of 4 hydrogens and 2 oxygens from here plus another 2 from here for a total of 4 oxygens. Now the question is, can I make the oxygen value, the number of oxygen atoms on the reactant side, 4 as well? Hopefully you're seeing that that's pretty easy in terms of just putting a 2 in front of my reactant O2, and 2 times 2 would give me 4. So having done that, now my oxygen atoms are balanced. Let's move on to a carbon or a hydrogen atom next. I'm going to go with carbon as my next rule, and the reason I do that is because I typically like to balance the hydrogens last. So if I'm going to start with carbon next, I would see that I have 1 on the product side and 3 on the reactant side. I need to get the product side to have 3 carbons. So I'm going to put a 3 down here. Just kidding. That would be wrong. You never ever mess with the subscripts. I am, however, going to put a 3 in the front of my molecule. And that 3 will distribute into the entire molecule of CO2. In other words, I now have 3 CO2 molecules present. So now my 3 times 1 gives me 3, but notice that 3 is also going to be multiplied by the oxygen present. Wah, wah. We just balanced oxygen. Oh, now everything's going to shift again. Shucks. Oh well, we got to do it. So now we have 3 times 2. That gives me 6 oxygens, plus the 2 oxygens, because of that 2 in front, that are over on the other molecule in the product side. So now I have a total of 8 oxygens on the product side. 1 step forward, make it 2 steps back. My, oh my. Now our carbons are balanced, but the oxygens are no longer balanced. We need to somehow get the oxygen on the reactant side to now be 8 like it is on the product side. So instead of 2 as my coefficient in front of O2, why don't I just make it now a 4 as my coefficient? So if I put a 4 there, 4 times 2 would give me 8, like on my product side. Cool. So now my oxygens are balanced again. See how I had to bounce from carbon back to oxygen to fix that? That's going to happen for a lot of these more challenging balancing questions. Okay, oxygen's finally balanced again. What about our hydrogens? I have 4 hydrogens on my product side and I have 8 on my reactant side. So let's try and fix that. In order to get 8 hydrogens on the product side, the only option I have is adding a 4 in front of my water. When I put a 4 in front of my water, that would give me the 4 times 2 that I need for 8. However, when I just did that, I just messed with our oxygen value again, because 4 is also going to distribute to that oxygen. So now I have 4 oxygens from here, plus the 3 times the 2 oxygens from here. So I need to add my 6 and my 4 together to now give me 10 oxygens present. Okay. So this last bit isn't as bad because now my carbons are balanced, my hydrogens are balanced. Now I just need to go back to the oxygens again and see if I can somehow get the 8 oxygens over here to now be 10. And hopefully you see that's a pretty easy fix. What times 2 gives me 10? Because this 2 up here needs something multiplied by it to give me 10. And hopefully you know that that number would be 5. So 5 times 2 would give me 10. Now, finally, I have 3 carbons on each side, 8 hydrogens on each side, and 10 oxygens on each side. That should be the final lovely answer of a balanced chemical equation. Let's try this one together to give you an idea of how to handle these polyatomic ions. They can be a little tricky, but just keep in mind that we're multiplying everything inside the parentheses and now also everything on the outside of the parentheses in front of the molecule. So here we're going to start by drawing our line, as always, between our product and reactant side so we can compare both sides. And let's tally up the types of atoms present. We have beryllium, Be, we have nitrogen, we have oxygen, we have Rb, and we have F. Notice that the bookkeeping here is going to be huge to make sure that we are staying on track. All right, how many of each do we have? On the product side, we have 1 beryllium. How about the nitrogens? We technically have 2 whole cookies of nitrate. So we have NO3, NO3. We have it 2 times. So that means I have 2 nitrogens, and I have 6 oxygens. I have 1 Rb and 1 F. How about the reactant side? I have 1 Be, I have 2 Fs, I have 1 Rb, not like Arby's sandwiches. I have 1 N, and I have 3 oxygens. Don't be frightened. We will get through this together, I promise. All right, so let's start by checking out which ones are unbalanced. Our beryllium is balanced, nitrogen is not, oxygen is not, Rb is balanced, and fluorine is not. So let's focus on one of those first. We don't have any weird, odd, even misconceptions, so that's good. But what we do want to focus on now are the atoms that are in the polyatomic ions. This polyatomic ion could throw us a curveball if we don't try and balance those atoms first. So let's try that first. Let's focus on trying to get our oxygens balanced. In general, with these really hard problems, oxygen's a good atom to start with overall. anyways. So we have 6 oxygens on the product side and 3 on the reactant side. The only thing that multiplies by 3 to give me 6 is 2. So if I locate where my oxygens are in the reactants, I'm going to put a 2 in front of that molecule. Now what I end up with is 2 distributing into this entire molecule. So 2 times Rb gives me 2 Rbs now. And 2 times N will give me 2 nitrogens. And 2 times 3 oxygens will give me 6 oxygens. Notice that by doing it this way, by starting with my polyatomic ion atoms first, not only have I balanced my oxygens successfully, but I also ended up balancing my nitrogens at the same time. Sweet. I did, however, screw up my Rb balance a little bit. I used to have 1:1, now I have 2:1. So let's focus on Rb next. We have Rb2 atoms on the reactant side and Rb1 atoms on the product side. So what times 1 gives me 2? I'll put a 2 in front of my RBF molecule. Now I can distribute that 2 into Rb and to F, and that gives me 2 Rb atoms and 2 F atoms. Well, golly gee whirlikers, looks like that ended up balancing the rest of our equation. Now we have equal numbers of each atom present on both sides. So there's your final beautiful balanced chemical equation. Think you got it? Think you can brave the polyatomic ion challenge in balancing? Go ahead and pause the video here and try it. And last but not least, let's give this one a try. Draw that line through your reactants and products. Let's tally up the atoms that are present. We have Na, we have O, we have H, and we have K for potassium. We also have P in this one for the phosphate polyatomic ion. Let's count up how many atoms we have on each side. On the product side, we have 1 Na. We have 1 plus 4, so 5 O's. We have 1 H. We have 3 K's, and we have 1 P. On the reactant side, we have 4 plus 1, so 5 oxygens. We have 1 P. We have 1 K. We have this H here, that's just 1 H. And we have 3 Na atoms. Let's compare both sides. We see that our oxygens are balanced, so are the hydrogens. Potassium K is not balanced. We have balanced P atoms, and our sodium, our Na, is unbalanced. So we have to pick one of these unbalanced ones to work with here. So we have the option of sodium or potassium to try and balance those two. It doesn't matter which one we pick to start with, so let's just pick Na. We need 3 on the product side, so I'm going to put a 3 in front of Na. Now that 3 distributes into all of the atoms present, so now I have 3 sodium atoms. I also have 3 times 1 for oxygen plus 4, so that gives me 7 for oxygen. And I have 3 times 1 for hydrogen, so 3 hydrogens. Now that our sodiums are balanced, 3 and 3, let's move on to our potassium before we try and mess with all the other stuff we just screwed up. Because now our oxygens are unbalanced and so are our hydrogens. But let's just ignore that little fact for right now and move on to our potassiums. Right now we have 3 potassiums on the product side and we need 3 on the reactant side. The way we're going to do that is by putting our 3 at the base. Just kidding, never mess with the subscripts ever! We're going to put a 3 at the front of our KOH molecule and distribute that in. So now we have 3 Ks, 3 Os, 3 H's from that one molecule. So let's see, we've got 3 Ks now. We've got 3 O's here, but we also have 4 here. So now we have 7 altogether. And if we distribute in, we have 3 H's as well when we do that. So we've got 3 H's in place where we distribute over. There's no H's over here, so we're good in that regards. Now let's go back and double check our balancing on both sides. Well, golly gee whirlikers, we can see that this right here is balanced after we did that. We do have 7 on both sides. And our H's happen to be balanced now after doing that. Awesome. We have balanced K's because that's what we just did. And nothing messed with the P's throughout the whole endeavor. So the P's are good. Looks like this equation is balanced. And there you have it, your lovely final product of balanced chemical equation. So the last 2, we just completed this one and we also completed this one. How about the rest of those equations? You think you could balance them? If you can balance all of these with ease, you know you've got this concept down and you're ready to move on to the next bit. Please make sure that you really understand this balancing chemical equation concept. It is a foundational principle to pretty much anything else that comes after this. And the next challenge that you may encounter is taking words and creating the actual molecules themselves in the equation and then balancing it. More on that in another video. If this was helpful for you, please give me a quacks up and subscribe to my channel for more educational content and to help others like you to find this educational content easier in the YouTube algorithm. Have a ducky day! Are you more of a visual person? You like to see an actual picture come into play when it comes to these obscure chemistry concepts? These PhET simulators might be just the thing for you. Let me show you what this looks like for the same exact chemical equation we were just playing with, but with pictures. We have our CH4, our methane, and our oxygen combusting to create CO2 and water vapor. So let's go ahead and put one of these on each. If I put one CH4, we can see that there is one carbon in the CH4 molecule and 4 hydrogens. So that's where these scales are a little tipped. You can see that. We're going to have one oxygen at least. So we have one O2 with 2 atoms of oxygen present. And then on the product side, so on this side of the balance beams, on the right-hand sides, we're going to add a CO2 and we're going to add a water. So right away we can see that there's an imbalance thing going on here. We've been showing that as a line through the middle and counting up our atoms on both sides and comparing the values. This is showing you kind of pictorially how these scales are not balanced on either side. We have 4 hydrogens on the reactant side and 2 on the product side. Over here, we have those 2 oxygens on the reactant side and 3 on the product side. Just as we did before, I'm going to manipulate the number in front of water, the coefficient value, and now add 2. So we can see that that balanced our hydrogens right away, and now we have 4 on each side, but our oxygens are still grossly imbalanced. So I need to go back to the other side, the reactant side, to try and add more oxygen atoms there. And the way I do that is by adding a whole nother molecule of oxygen, again, never changing the subscript numbers, always the coefficient value. And that's how we get our balanced chemical equation. You can see here in the pictures as well how all of the red spheres, gray spheres, and white spheres add up to be equal on both sides of our reaction arrow. If this PhET simulator is helpful, I've included the link in the description below for your convenience.
No ducks, no glory.